All right, so today I'm gonna bring you guys a talk called Building Autonomous Rideshare Vehicles, or in general, autonomous vehicles. Where are we now? So I would like to look at a little bit of the past of the autonomous vehicles. What are we currently at, and what are some of the future problems that we need to address so that autonomous rideshare vehicles can be a thing? This presentation is done on behalf of University of Toronto's aUToronto, where we are a autonomous self-driving competition team that participates in the SAE Auto Drive Challenge. So a little bit background about aUToronto. So what aUToronto does, aUToronto, we are a student-run autonomous vehicles team. So the composition of the team is 100% student. Plus some faculty advisors and advisors from General Motors. So we are actually a competition team sponsored by GM, which you can also see on my virtual background. That's the vehicle General Motors donated. It's a Chevy Bolt 2017 model Chevy Bolt EV, and we sort of modified it into I will say an autonomous vehicle under certain operation design domain. Team aUToronto composed of quite a large number of students. We have about 100 students for the last year. And then the ones you see on the photos are the team's flight team. So we're basically the core of the core members of the team that is supposed to know everything and being able to address all the issues. So we get to go to Michigan actually a couple of weeks ago and then participate in the competition. And this is our fifth year that we have win. And this year we have win every single category. Except for two that we didn't win first place. We won second place, and the other we won third place. So we have a very good track record. And then this is the system in there is our competition design for this year, which is sort of a test platform for a proposed perception system. So with that being said, I want to talk about a little bit about autonomous vehicles. So the presentation today is actually a mix of a couple things. One is the autonomous vehicle that we designed in the past 4 years. The top left one, which is called Zeus. The other thing focus is the perception test platform, which we built this year. Which will transform this perception test platform into next year when we get a new 2022 Chevy Bolt EUV. We'll basically put it onto the Bolt EUV and then try to make it autonomous driving capability. Certain aspects of the work we do is technically speaking under the NDA. So for those aspects of the work, I might not be able to share too much details, but there are plenty of resource online that talks about autonomous vehicle design, namely Waymo. So some of the demonstration are basically based on Waymo's public available resource for that. So with that being said, I would like to talk a little bit about today's agenda. So we did the introduction just now, and then next I'm going to talk about the autonomous vehicles history, the definition of autonomous vehicles, and some of the modern day example for the autonomous vehicle. And then I'll mainly focus a little bit on talking about autonomous vehicle sensing technology. So the sensors that on the autonomous vehicle. I will try to touch a little bit about autonomous vehicles software system architecture and the software components, although certain areas do have a slightly higher technical background needed to understand, but I'll try to explain it as much as I can without involving math in the conversation. And then lastly, I'll talk about why are we or where are we in this process where you'll see so many companies trying to get to level 4 autonomy, and some of them might claim that they have what quote unquote full self-driving. So we'll talk a little bit about where are we actually from an academia standpoint, where we are in this process. So with that being said, let's start with talking about a little bit about autonomous vehicles, the history, the definition, and examples. So in contrary to most people's understanding, autonomous vehicle actually started its way back in the early 1980s, where there are a couple very industry pioneer that sort of started this process of developing a hands-off autonomous vehicle system. Namely, in 1980s, Carnegie Mellon University developed a vehicle platform called Nav Lab, which is the leftmost vehicle. It's modified from, I think, a minivan. The vehicle actually performed only one task by then, and it was already a huge groundbreaker. What it does is basically we're able to keep the vehicle within the two lane. That's all it does. Compared to modern day technology, if you have buy a car in recent years, it's sold as the feature of lane keep assist, basically. So, and it's also, if I recall correctly, a single agent system. What that means is it assumes there's no other road agents such as vehicles or pedestrian. It's only by itself, and all it does is keeps within the lane. But mind you, it was in 1980s, so back then computers are not as powerful as modern day computers. Even modern day, like one of our CPUs can compare with some of the supercomputers back then. So, and then autonomous vehicles really sort of develop slowly until the facilitation from Darpa, which is a U.S. Government agency and military affiliated, where they try to accelerate this process by hosting this challenge across universities. In 2004, it's called Darpa Grand Challenge. In Darpa Grand Challenge, teams were basically able to do sort of a mock-up system of how they would make a vehicle drive autonomously in a desert area. I think it's in Arizona, but I might be wrong. It turns out it's actually a very hard task with the technology back then. Camera technology is there, but the other sensing technologies that you will hear very commonly nowadays, such as Lidar, are not that well developed. So the 2004 Darpa Grand Challenge was quite a bit struggle for a majority of the team, but several of them still stands out and somewhat complete the challenge. It really isn't until 2007 where Darpa Urban Challenge happened. Universities like Stanford, Carnegie Mellon, I think MIT was also a participant, started to participate, and then you can see more modern day sensor technologies featured on their vehicle, but then there's still some sort of old school technology such as 2D Lidar, which we'll talk a little bit about in the later slides. But this is, I think, featuring Stanford's submission for the Darpa Grand Challenge, and a lot of groundbreaking technology such as multi-line Lidars were sort of facilitated utilizing this competition. And that brings up to in 2012, where Google Project X started publicly testing their autonomous vehicle project. Although the development of the Google Project X actually started right after the Darpa Urban Challenge. So it's Darpa Urban Challenge in certain people's mind, including mine, is sort of the ground zero of modern day autonomous vehicle development. And in 2018, Waymo becomes the first company amongst several other few started to publicly testing the concept of autonomous rideshare system in certain areas. under operation design domain. I'll talk about the operation design domain, that concept, a little bit later. But in a specific area, I think it's Phoenix in Arizona that test their systems and allow users to ride their vehicles with a safety driver in the seat. In the same year, something super unfortunate happened in US, which is the first fatality accident on a level 4 autonomous vehicle happened. The vehicle was owned by Uber ATG. This also sort of becomes a turning point of the discussion from just building an autonomous vehicle quicker and then win the sort of the arms race to more reflection on safety on autonomous vehicles. And fast forward to 2022, the safety of autonomous vehicles is still a very crucial aspect and discussion point on the topic of autonomous vehicles. So I sort of mentioned the term level 4. The level is actually a definition of autonomous vehicle autonomy by SAE International. I think it's a standard for automotive engineering, which they're like a governing organization on automotive engineering. So they define 5 levels of autonomy in a vehicle. So for level 0 to level 2, on a very high level summary, as a driver, you still need to pay 100% attention on the road, and you have to constantly supervise the vehicle. You cannot zone out or I would say not drive the car for a prolonged area. The car in level 2 might have features such as providing steering and the brake acceleration support, such as following in the traffic jam, the stop and go feature, or they can have a lane centering feature, which keeps your car in the center of the lane. So a keyword you might hear if you buy a vehicle recently for like an add-on feature called adaptive cruise control. Level 2 is also very popular these days. Most auto manufacturers, such as I'll say Toyota, Volvo, or BMW, they claim they have level 2 features, although the performance of them vary drastically. For level 3 autonomy, it's a tricky one because level 3 autonomy basically defines that the vehicle will request you to take over if the vehicle thinks it is in an area that it cannot handle. And then for the SAE level 4 autonomy, it's a more cautious definition of autonomous vehicle, where technically speaking, you are not driving. However, for level 4 autonomy, there's a rigorous condition that needs to be met for the autonomous vehicle to operate. However, as humans, you do not, technically speaking, need to take over control if the vehicle are running into hiccups. And the vehicle should be able to gracefully degrade, which is a fancy word for saying stop itself. Obviously, you cannot just stop in a highway, obviously. So the degradation is a very broad term definition of sort of exiting the autonomous vehicle. And then for level 5 is the goal everyone trying to go to, which it envisions a full autonomy capability, and the conditions bounded for the level 4 autonomy is lifted. So you can drive, you can take the car, or in other words, the car can take you to anywhere you want it, and without any hiccups, or even if there's hiccup, then the car can handle it themselves. So that's the definition of the SAE level of autonomy, the J3016 standard. So for modern day autonomous vehicles, or more specifically for modern day autonomous rideshare system, there are a couple big players. Waymo, or formerly known as Google Project X, was the first to start. They started in Phoenix, Arizona, and I think they have now moved further to San Francisco in California and a couple other regions for sort of small-scale testing. Two new players rised up in these years. Apollo, that's a company from China under Baidu, and Cruise under General Motors. So both of them started publicly taking rideshare in given geographical region earlier this year. And if you actually look very closely, you will notice the Cruise car is also based on a 2017 Bolt EV, similar to what we have for our Zeus vehicles. So there's a couple of things that is in common, and there's a handful of things that is totally different, comparatively speaking. Another question when you talk about autonomous vehicles that has to be addressed is, why autonomous driving? Why would we want to sort of give up the fun, per some people's mind, of driving to autonomy systems? It turns out, actually, there are multiple studies that can back this theory, is that autonomous driving can further improve road safety. If the implementation is done right, the reaction time for an autonomous vehicle is much faster compared to a human driver. It can also increase productivity. Imagine one day when level 5 autonomy is out there, and you don't actually need to drive. If your commute is 30 minutes to your work, for that 30 minutes, you can do all sorts of things. But obviously, I strongly urge you not to do vehicles these days, because none of them have that capability to deliver the safety idea. It can also increase accessibility. So for some elderly people where they might have to have someone drive them to some places, they now can use autonomous rideshare vehicles to bring them to where they need to be, such as a doctor's appointment, or just go outside where they're living and then have some entertainment. Autonomous driving can also reduce cost, although this is a sort of a double-edged sword, where if you reduce costs in like cutting costs from paying a human driver, some people will be not happy, and they will lose their jobs. So this becomes really quickly a double-edged sword. And then lastly, and this is a very well discussed point, and nobody can draw on a conclusion, since we will have to see how it turns out, is that autonomous vehicles can reduce congestion. Although it's pretty obvious that when we reach a 50-50 split of autonomous drivers and human drivers, the congestion situation might actually get worse. And for some scenarios where autonomous vehicles were not considered, the road safety might be jeopardized. So it's interesting that we should see how things will turn out in the next couple of years or next couple 10 years. So next, let's get to a bit of sort of a little bit more technical discussion about autonomous vehicles. So we'll start with talking about autonomous vehicles sensing technology. So we'll start with first talking about Waymo's autonomous sensor system. So at least in the academia world, Waymo is considered as sort of the reference design of autonomous vehicles, since they're the first one enter level 4 ride sharing, and they're constantly improving their design. So what is on a Waymo's autonomous vehicle system? Well, turns out Waymo first have a 360-degree Lidar on top, and then underneath that Lidar, they place multiple cameras, actually in a 360-degree configuration to provide full coverage around the vehicle. And then for the long-range cameras, they put some long-range cameras in front of the vehicles to enhance looking forward. And they also put radars up top. They also have a handful of perimeter perception system, which surrounds the full vehicle 360. This allows the vehicles to basically have zero blind spot around the car. So it's actually a pretty impressive engineering design, considering the amount of sensors, the amount of reliability it has to be passed, and the redundancy that it needs to build an autonomous vehicle. So we've seen the impressive one. Let's talk about some of sort of our design. So keep in mind that the vehicle system we design is participating in a challenge similar to Darpa challenge. It's called SAE Auto Drive Challenge. Basically, 10 universities built their autonomous vehicles, and then we tested at University of Michigan's M-City Proving Ground to validate our vehicle's capability. It's a subset of a full autonomous driving problem, as you will see in a couple slides later. What we have is only sensor system on top of the rack. And if you pay close attention to the next slide, our sensor system actually mainly focus only on the front. We don't necessarily perform 360-degree surrounding coverage on our vehicle, since the competition is a single agent competition, which means other than you're the only one driving on the road, and the interaction of your vehicle compared to the other road agents are minimal. So that's how we can get away with our design. It ties into, again, the discussion of ODD, Operation Design Domain, which I will sort of formally define it a bit later in the slides. So our Zeus vehicle system have a Planix GNSS INS system, a Velodyne HDL64E Lidar, which for this one, most of the autonomous vehicles you see 2018, 2019 have that. It's sort of a standard design. And then we have a handful of cameras providing coverage on there. Note that we actually don't use radar on this version of the design. And fast forward to this year, this is so for the competition, it's a 4-year per round competition. So this year marks a new round of the competition, and there's some more new rules that implemented. So for lidars, we have to use Cepton's micro mirror technology lidar. So we no longer use a giant 360-degree lidar. And then this is our sort of test of and validation system we designed over the past year, and then it has achieved a very good result for the competition. The system utilizes 3 lidars on the top to provide a similar coverage looking in front of the vehicle. The same GNSS INS unit on top, on the rooftop, and then the similar configuration except more compact for 4 camera configuration, 3 wide angle and 1 long range camera. For our radar, we have 3 radars providing coverage on the bumper area, since you don't necessarily have to mount your radar very high, at least the brand we got. And then we also put another additional lidar on the bumper to again minimize the blind spot. Keep in mind that this design is also under budget, and what we are doing here is a minimal viable design, which that is basically a design system that is sort of with the smallest amount of money that we can design to provide the maximum performance. So this is what we had for this year. It's not on the autonomous vehicles or a car. It's just on a push cart as a test platform. So what are we gonna do next? So this is actually probably also one of the first times we have shown this publicly. This is our design for the next year of the competition, where we'll feature obviously more lidars to provide more coverage and minimize more blind spot. We'll use 6 lidars in total. And then 4 cameras, and then 3 radars, and plus a GNSS INS system on the vehicle to provide about a full 180-degree coverage in the front. So if you look at the 2 slides, you can see the design is pretty much transferable that we built. So let's take a look at the sensing technologies one by one. So obviously, most of you probably already know cameras, how they look like. You can actually see objects and recognize what they are very easily through camera. The technology is very mature. And in here is an example of our system's view. So we have 4 cameras. We're showing 3 of them. The other one is just looking at the trees. So it's a little bit boring, so I'm not showing that. And you can see there's the speed signs, 10, 5, and 15. You can see it's a little bit iffy on a wide angle when an object this is about 40 meters away from us. But we have a long-range camera here. So you can see with the long-range camera, we're able to see things further. So for cameras, you're able to tell what an object is or what type an object is very easily. However, you cannot easily tell how far away an object is from you because it's a sort of a 2-dimensional sensing technology. Obviously, Tesla has more cameras, more data. So you can, technically speaking, infer depth out of the cameras, but you have to have the large amount of data samples as they do. So that's a different discussion in academia where it's called monocular depth estimation. But for us, we rely on a secondary sensing technology called Lidars. So if you follow technology news, this term you probably have heard it several times, or I have just mentioned it a couple of times. So what is LiDAR? So LiDAR basically provides you something called a point cloud, where it basically describes the world with points. And then through these points, in this image, you can roughly tell this is probably either a tree or a lamppost. There's a car there, some more trees there. This is the LiDAR technology. So back then, a very popular modality of LiDAR is called a spinning LiDAR, or there was not an actual academia name. It's just what we previously used. I usually call them the spinning LiDAR, which involves a mechanical component that will spins around a component. How LiDAR works is basically it shoots out a laser getting bounced by a mirror that is movable, so you can change the reflection where you want it to shoot toward. It shoots on an object, and then the laser returns it back to the mirror, and then it gets onto a receiver. And then through how long you shoot out this laser beam, and how long it took for it to travel and bounce back to the receiver, you then can very easily tell how far away an object is, and that becomes a point on a point cloud. It's similar to how you point a laser pointer at some object, and then you'll see the light bounce back on that object, except in automotive LiDARs, they're on a wavelength that is safe for eyes, and you cannot see it by your eyes, but the sensors, the receiver chip inside the LiDAR can see it. So this is another example of the LiDAR right on my virtual background. You can see there. And then this is how a Velodyne 64 LiDAR works. It involves, it's actually quite an engineering marvel back then. So, and as you can see, it basically spins to provide the 360 degrees surround view. What it does is it uses 4 groups of 8 laser emitters, and then 2 large receivers, as you can see on the image, to receive the points, and then it spins on top of the vehicle, providing 360 degrees LiDAR coverage. This was for a long period of time the standardized industry standard for LiDARs. However, as you can probably tell, there's a lot of moving mechanical components involved in these LiDArs. So a more modern day LiDAR systems, we involve a little bit more called a solid state LiDAR. So a very sort of popular brand these days is called Hesai's AT128 LiDAR. In fact, a couple of the car manufacturers already integrated their LiDAR system on the vehicle. So it's one singular unit. What they have is a MEMS chip to shoot out the laser and then receive it. So there are no more majorly mechanical moving points that can mechanically fatigue throughout a long period of time. And then it's more preferred by automotive applications. For us, what we use this year is another different LiDAR technology called micromirror technology, in which the LiDAR have some mirrors inside that vibrate. And then you can see it produces a decent enough coverage for the objects, but it has this very interesting grid-like patterns. That's a very unique sort of characteristics of the micromirror technology, at least in this day and age by Cepton. So another very popular sensor modality on autonomous vehicles or a standardized formula autonomous vehicle construction is a radar system. So unfortunately, we're not allowed to talk too much outside for the radar we specifically use, but Waymo's, this is a demonstration on Waymo's vehicle's radar system. They actually have a very fancy system that allows you to process the radar image as radar's information as a Doppler range image, and it's more human readable and machine readable compared to what we have. So for what we have what's called a radar target point. So this is an illustration of radar. So you'll see we get similar to point cloud, except these points are much sparser and they sort of float on the radar surface of the objects. And then with radar, sometimes you get ghosting effects and a certain multipath reflection effect, which are two big words, but just think it as points where they shouldn't be there, but they are there. And for radar, the advantage is that you get back the object velocity directly alongside with their position information. So each of these dots actually contains a velocity information that you can read on our radar system. So how does that work? So it turns out it's actually a very, you can go very deep into the mathematics, or you can very easily understand it as you shoot out similar to LiDAR, you shoot out a radar 77 gigahertz beam, and then when it hits an object, it will bounce back. However, if an object is moving, the frequency will change. And then through that frequency, or the Doppler effect, you can infer the vehicle's velocity out of there. So think it as when you're standing on a street and then there's a police car with sirens driving fast next to you, you'll hear the tone shift a little bit. That's basically on a very rudimentary level, similar idea of how automotive radar gets the velocity information. It looks at the frequency shift. So for some of you, if you follow technology, those are very standardized sensing technologies that has been out there since early 2014, 2013 even. Next, I'll show you a little bit of sort of the bleeding edge technology of the sensors. Fmcw Lidar, or four-dimensional Lidar, is sort of a new thing, comes out recent couple years, namely the company called Ava, that produces sensors for that. This is from their website. So as I previously mentioned, LiDAR can give you a three-dimensional position with respect to where you are of an object, because it shoots out a laser and look at the laser bouncing back and calculates where it is three-dimensionally. Radar gives you instantaneous velocity. So why don't we combine the two? It turns out you can actually also using laser to look at sort of this in a very, very broad scope of a frequency shift in the laser space, and you are able to get both the good point clouds as well as you can get the velocity information of each point, which is super nice. Another technology that hasn't really been put onto autonomous vehicles due to its import and export restriction is infrared cameras, because military still uses some of these technologies. But it also allows you to see objects very good at night times, especially handling animals that jumps out of the side of the road. So we're hopeful that this technology can get opened up a little bit more, and more vehicles can have that. And then lastly, there's the spinning radar. It's basically a two-dimensional scan of the environment using the radar technology. So as you can see here, you can roughly tell the outline shape of the object. And then this is one of the test vehicle U of T have. It's called Boreas. And then as you can see here, you can pretty much tell where the objects are, similar to Lidar, but this is on a radar sort of domain. So when talking about designing sensor suite for an autonomous vehicle, another very important aspect you need to think about is the sensor coverage. So Waymo have a full 360 coverage, nooks and crannies around the vehicle. For our vehicles, so for Zeus, we have a 360-degree coverage, that's introduced by Lidar. Our camera only covers the front 180. We did attempt to put radar on there, but eventually we didn't use that. So that's the Zeus coverage. And then for the perception cards coverage, you can see here. So our cameras provide about 160 degrees horizontal field of view. Radar is about 180, and then Lidar is about 150. This is all the sensors on the, so for the camera and Lidar, this is analyzed using the top sensor rack, and then the radar is using the bottom one. So how can we get away with only having that little sensor compared to Waymo's design? Well, I have to introduce the concept of operation design domain. So what that is basically operation design domain defines a set of operation areas that your vehicle is expected to handle and operate in. For our scenario, it's very simple. It's based on whatever the competition gives us. All we need to do is drive within the lane, detect traffic light, handle pedestrian crossing the crossway, and also there's only one pedestrian expected at given time, and then handling deer jumping out of the road in front of our vehicle. So that is our operation design domain. And then in here, you can see I previously mentioned that there's also for actual autonomous vehicle company, there's a geographical fence idea where Phoenix, Arizona is the first area it validated because it's most likely always sunny there. Although Waymo nowadays has also expanding their weather coverage to pretty much everything, but a safe approach is you define your operation design domain and then validate it rigorously, and then slowly expanding your operation domain. So that's why we get away with what we have, and that's a very important concept in autonomous vehicles. In the upcoming years, you will see cars selling autonomous driving features, but then they only support in certain areas of a geographical region. That is also bounded by the operation design domain. And some cars might not work under rainy weather or snowy weather. So that's like a very important thing to look out for. So I'm running a little bit slow on the slides. I guess I'll pick up my pace a little bit. So next, let's talk a little bit about designing the system architecture of an autonomous vehicle, or what I call for a old school autonomous vehicle. These are the components in it. Modern day autonomous vehicles are more complex or have more variations, such as they have machine learning end-to-end. That's what Tesla does. Or like some more rigorous component level machine learning that is basically treating the system as a black box. So a very basic robotics system it can be defined as follows. So you have a world or a plant that you have your sensors on your vehicle, you have your actual vehicle, and you have the actuator or motors or execution components on your vehicle. Your sensors look at the world, do something called a perception or perceive the world. From the outcome of the perception, you make a plan of the based on the perception. You hand it over to control, and the control execute the plan, and rinse and repeat. Here I show a very high-level summary of our autonomous vehicle system architecture for perception this year we designed. So basically, our camera is only responsible for telling if an object is an object and what type an object is. So for example, the cameras only tell, hey, this is a sign, hey, this is a barrel, hey, this is a car. Our LiDAR only tells, hey, I've seen something at this position. And our radar basically is responsible for telling, hey, I see something at this position with this velocity, roughly. And then it's all up to our sensor fusion component to mix the sensors together, information together, and produce a proper perception. So for all these components to talk to each other, what we use is something called a ROS, ROS Robot Operating System, as our communication middle ground. So how can we have sensors talk to each other? It turns out ROS is very good, provides a very good communication layer for our components to talk to each other. And if you're interested in going into the robotics world in the future and you want to learn up some programming skills or some basic knowledge, ROS is basically, if you go to a university or a college to learn robots, you will definitely cross paths with ROS. So if you're interested, I urge you, to practice using ROS components and simulators and robots. So our detection layer, as I talked about earlier, cameras is responsible for seeing the object in the scene. On the left, it shows how we see these speed signs. And then on the right, we show the point cloud there. And then we show, what we use is called a clustering. Basically, it looks at how many points are close to each other. Then they're a cluster, so there got to be an object there. So it looks at the clustering based on the point distance. And then, so as you can see, this is without the bounding box. You can see there are three things. As us humans, it's very easy to tell there are three things and then two things over there. So yeah, it do a clustering and generates a localization output. And then for this scene, it's kind of boring because all the objects are stationary. So there will be, for example, a target registering on there saying, hey, it's a zero velocity target. So how do we combine these information together? It turns out it's actually a more complex problem than we think, and human brains can do this super well, but not for a computer. There's a couple of things we need to address. First of all, we need to solve the problem of having all the sensors talk on the same time scale and time point. So imagine if you're driving on a road and then you're driving very fast. You have seen a sign already, but your buddy is driving slower than you. So they haven't seen the sign. And then you try to talk to him about that speed, about that sign, about that information sign. Your buddy will probably have no clue because they haven't seen it, or that you are not talking on the same timestamp. So time synchronization is very important in the sensor fusion. This is a very detailed explanation. I'll just quickly highlight something. So we use what we call PPS and MEA signal, which is the information you can get when you connect to GPS constellation, that all the satellites have a very, very good crystal clock on there. And then they can provide very, very, very accurate time. And then we use that time to basically tell all the sensors what time it is. And then these sensors, when they provide the observation, they use that time. So that's this whole system does. Another very important aspect that we need to talk about is basically the coordinate frame. So different perspective, different sensors have different perspective. Imagine you're standing in a room facing slightly different than another person standing in the room. Things at your 3 o'clock direction might be at someone else's 4 o'clock direction. Even though it's the same thing, it's only because you guys are standing at a different place of the room facing differently. That's the concept of coordinate frame in a nutshell. Obviously, if you really want to drill deep into this, there's plenty of linear algebra matrices involving that. For the interest of time, we're not going into that. And another thing I want to quickly talk about is, so you have this sort of perspective difference. How do you solve it? Turns out we can use something called iterative closest point. And again, I'm not going into the math, but I'll give you a very high-level summary of what it does. It basically looks at the object, trying to find the best match, how you can overlay 2-point cloud or 2-point series. It doesn't have to be a point cloud, 2-point series onto together, so that the difference between the two objects is the smallest. So as you can see on the left, you rotate a little bit of the bunny. The algorithm, the ICP algorithm, obviously there's a lot of variations on improving that, but the old school ICP algorithm will just match it. So this is a good example where you pull it away, and then it's gonna try to find the best match. Think it as trying to match the scene. Obviously, just like the toy game of putting shape into the bin, it can break because sometimes certain aspects of the shape do look very similar to each other. So that's the ICP algorithm. So now you know what ICP is, then you can probably understand this a little bit better. So now we have two sources of information. We need to find the description that will align them in the sense of everyone is talking the same perspective. It turns out when we have 4 Lidars, and then each Lidar is mounted differently, pointing differently, we need to do ICP so that we can generate this very nicely calibrated scene that you can see all the Lidars are describing the same thing in the same frame. And then you can also, through some very not that complicated geometry, but some geometry and matrix manipulation, you can also project that point from the Lidar onto your camera. And then now you can suddenly describe both information at the same place for the same thing. And then just like as I mentioned, you can also technically match just points onto points, or in this case, trajectory onto trajectory. So this is how we do the LiDAR and radar calibration. It's actually quite fun. You have someone running in front of the sensor system in a weird S-shaped trajectory. And at the end of the day, since it's the same object, both your sensor system should, both from LiDAR and radar, should all have this trajectory described for that same object. And then from that, we are able to pass the information onto each other. And then we're able to provide this sort of information in the unity, sort of like in the same uniform descriptor. And sort of more visually illustrating this. So this is me walking in front of our LiDAR with our camera. You can see our camera both see me, and our LiDAR also see me. That's sensor fusion in a nutshell. And then there's a human standing there. This is the LiDAR, and you can see the human gets picked up the pattern. So you can lay the points on the human. And then once you have those information through some very fancy math, or actually technology that dates back into 1980s, you can basically track the object. And you can see each object have their little unique identifier number for that. So yeah, that's the perception system in a nutshell. For the next couple ones, I'm probably going to go a little bit quicker. So for localization, basically, this is a demonstration of lane detection. It uses some very traditional computer vision algorithm called Kenny Edge detector and half line. That it will propose a bunch of lane proposal. If you drive and you have used those fancy ADAS features, you will notice in certain areas, the lane detection or the lane keep assist just keeps freaking out because, as you can see, this is probably another example of how things are done. Yeah, this is another localization. So it turns out you can use GPS and a map, similar how us humans do. Or you can use LiDAR to do localization. through the method I previously mentioned, similar to the ICP idea. You have a point cloud you try to match to that will just gives you a description of where you are. Or you can even further abstract it higher to just using the lane marking instead of having the full point cloud. Next, I'll talk a little bit about the planning aspect of things. So in a nutshell, planning can be dissected into 3 problems. You have a global planner. The global planner's responsibility is to tell you how to go from A to B. For example, imagine you're at your home and you want to go to your school. The global planner will tell you, hey, you should take, let's say, road A, and then road B, and then road 3, and road C, and then that will get you to your university. A local planner, however, is more specific to the local segment of the lane. For example, if you're walking on the road A, but then suddenly, let's say there's an obstacle on road A that partially blocks the road, as illustrated on the right example, so you have to drive around it. That's a local planner's responsibility. And then finally, for an autonomous vehicle, you also want your vehicle's trajectory, which it describes how it drives around, to be smooth and comfortable. Obviously, you don't want to sit in a car being driven like a roller coaster. So you also adding like a velocity profile generator and a path optimizer to basically make your car that's comfortable to ride. And then this is a quick demonstration of our planning system from round 1. We haven't built our new planner yet, so this is how we manipulate a parking maneuver. So you can see the proposed trajectory is actually very, very smooth here. And then with all these put together, you get to have an autonomous vehicle. So as you can see here, I'll just show you a couple examples. So as you can see here, it's going through a corner. So you can see how we maintain the speed of the vehicle. But then also, like you can see, we keep on road, and then the driver there is just for the safety purposes in case the car goes wrong. And then here we hit 20 miles per hour speed limit. So obviously you don't want to be the person holding up traffic. So you can see our vehicles speeds up accordingly. And then the road is a little bit swervy here, so it goes around. And then it reduces speed since there's a speed sign of a speed limit 15. You can see it actually starts braking even before it hits the point. Once it hits the speed limit sign, it goes according to the speed limit. So here it illustrates our round 1's final vehicles of pickup and drop off. Due to COVID back then, we can't have 2 people in the same car. So this is just a demonstration. Now the cool part is once the car drives further, there's a deer right there that will sort of jump out of the road. And you can see our system actually recognizes that's a deer that has a velocity. So it expects it to jump up and sort of takes the maneuver ahead of time. Here's another example. So you can see the car sort of misses the deer. So that's our system. So let's talk a little bit about where we are now. So 3 main problems in my mind of autonomous vehicles nowadays. One is most modern autonomous vehicles are built sort of a scenario by scenario cases. So if you've seen a scenario that you have not seen, you add it into the scenario bank, and then hopefully your system will learn how to adapt to it. But we all know there are infinite possibilities in the world. So how do you solve that problem? Another thing is adversarial weather. This is another main reasons why autonomous vehicles hasn't been in Toronto, but most of them developing sunny California or sunny Arizona, because there's no rain, sun is super bright, road is pretty well painted. But in Toronto, it's quite challenging actually. And U of T have a research group. Actually, my affiliated research lab, we're starting the Winter project, which hopefully can bring autonomous vehicles into Toronto and Canada. And then another thing is proof of safety. Since 2018, Uber ATG's incident, safety has been a highly emphasized area that it's an area that people cannot overlook. And then lastly, with safety, with scenarios, how do we sort of introduce the public perception and public acceptability? So some people will lose their job because autonomous vehicles are a thing. How do we convince those people these are the better changes? So for adversarial weather condition, it happens. So here's an example. So you can see all those points all over the place. These are caused by snow. So you have to have a way to clean up the scene. And then in Toronto, if you're in Toronto, you'll notice the snow and salt mixture will adhere to your window, and then they become very bad stuff. So this is our mechanical engineer. This is our proposed sensor wiping system, as you can see there. So are these systems effective for our vehicle system? Another thing is nighttime driving. This is what the discussion on Tesla is mainly on. So cameras don't necessarily see well at nighttime unless you custom build some imaging sensor that handles that. So having multiple sensors is definitely a plus, ensuring more safety autonomous driving for sure. And let's talk about corner cases. So I'm gonna play a clip here. This is from Waymo. I don't know if you can tell what's happening on the screen, but what happened is there's an elderly lady sitting on an electrical wheelchair, and she's chasing a duck. So this is sort of a very textbook scenario of how do you handle motion planning? How do you handle scenarios like this? Obviously, now some companies will be like, oh, we'll create a scenario that have someone on an electrical wheelchair driving randomly on a road. But how do we expect these scenarios before we even put our vehicle on the road? And then this is another very funny video. So how do autonomous vehicles handle police pullover? Well, it turns out it can't right now. As you can see here is a scenario where the autonomous vehicle just literally evades the police stop. And the policemen have no clue why the car is just driving by itself and there's no driver in it. So both the public perception and corner cases like these, how do you encounter a police stop where the police is just doing human being things that's non-predictable? And this happened to our vehicle. How do you handle animals running to vehicles? It's technically speaking not our fault, but we could have done better. We could have stopped earlier once we see there's a deer, or we could have just go faster and not go into it. Well, it turns out a modern day solution is you just build a simulator and then let the car go and let the agents play with each other, kind of like a TV series back in the early 2012s called Person of Interest, where you just build a huge number of automated scenario generator. What you're seeing here is one of the scenario generator we built that randomizes the scene. For one scene, the car might jump out. For another scene, the deer might jump out. And for lastly, you see here, a pedestrian jumps out in front, and our car needs to handle it. And for bigger companies such as Waymo, they're obviously going to be more fancy on that. They have sort of learned AI agents. So similar to those you play in the Grand Theft Auto, those AI agents, but now they're actually more human-like. And then you put your car into those agents and let them just interact with each other and see what comes out. And then autonomous vehicle safety, as I mentioned previously, is very important for public perception and public accepting the autonomous vehicles, and just in general, people trusting to use them. So the traceability is a very big discussion point, where we can go from laws to specification to implementation to its behavior and back. Those are old school systems. With modern day systems, which are all machine learning trained as a black box, the traceability is a little bit harder to explain, although work has been done on that front. Explainability. So how do we know why the car did something or did not do something? Similarly, you need to explain certain behaviors of your car. And then lastly, how do you audit the system by the government agencies such as DMV? So for us human drivers, you have a driving test. Should autonomous vehicles have a driving test too? So with that being said, some closing remarks. So I know the audience is mainly for high school students, and I think there are also some undergrads in the call. So there's still quite a large number of work to be done in the field of autonomous vehicles, addressing the discussion of generalization. Don't just feel looking at, for example, what Waymo has done and think autonomous vehicles is there, or look at what Tesla PR have said. It's actually farther than what we think commonly perceived autonomous vehicles is to us, if you factor in the discussion about safety and generalization. So I encourage every one of you, if you want to pursue the field of robotics, or even more specifically autonomous vehicles, to always keep in mind that you're building an engineering product that is used by going to have an impact on thousands of people's lives. And then safety should always be your first priority when you design a system and learn certain aspects. And also learn good math, because you will have to use it for almost everything. But yeah, and that's the end of my presentation. Thanks everyone for watching. If there are questions, we can put it into the Q&A post, and I'm happy to answer them.